Hi, so the idea with this video is to help you out with Lab 9. In Lab 9 you're going to make a serial adder. If you were one of the few people who came to class on the day that I taught it, then you'll know all about serial adders. Otherwise, you might not know how they work, and if you don't know how they work, this lab is going to be really hard. I did record the lecture, so if you want to see it, if you go to the Moodle under SI Resources, it'll be right above this video once I post it. So at the bottom we have the serial adder class, and so that's just the recorded lecture from the class where I talked about serial adders. So the way serial adders work is you take two numbers, and they can be as many bits wide as you want them to be, and you add them bit by bit, and you do this as a finite state machine. And this particular lab is not hard in concept if you understand a serial adder, but there were a few tricky parts that I struggled with to make sure that I got them right, and so I want to make sure that I help you with those. So when you look at the lab, you have a brief description of what a serial adder is. It performs binary addition bit by bit, and just real briefly, because I do this in the other video. If you have, let's say we've got two 4-bit numbers, and then we'll have our sum. So this will be A and this will be B. You're basically using a shift register to shift out, and I don't remember off the top of my head if you're, you'll be shifting the least significant bit, so you'll be shifting from the right. So you're shifting this bit out, so you're getting that bit, so you'll be getting A0 and B0, and then you'll be shifting and you'll add those together, and that'll give you your sum, and you'll be shifting that into your sum. So like if this is 1 and this is 0, you would add those together to get 1, and you would shift that into here, and let's say this was 1 0 1, and this is 1 1 0, and then you would shift these out and shift these over, and we have 1 1 1, and you'll fill in with a 0 1 0 1, fill in with a 0, and then you do this bit by bit until you make the sum. And so the sum is going to be building as you go through, and you have to keep track. You have to count however many times you'll need to shift in order to get your result. That's going to depend on whether you use a Mealy serial adder or a Moore serial adder, and as we know, Moore has more states than Mealy. And what's nice about this is you have already the code that you would need for a Mealy type serial adder, and your job is to adapt this to be for a Moore serial adder. So let's take a look at what the book has. So the book has, first of all, it has this code that is for a shift register, and this is very good code, so this works. Now the n equals 8, the parameter, tells you how wide your register is going to be, how many bits it's going to be. In this particular lab, you are going to be dealing with 3 bits. So you're going to make the shift registers 3 bits wide. So you'll want to use this code, and you'll want to make n equal to 3. And other than that, this code works just fine. So this, what it does, it has these inputs and outputs, and R is what you would load if you need to load it. L is the bit that tells you whether or not you're loading or not. Let's see, so Q is your entire register. So Q is all of the bits of your register. Clock is obviously the clock. And W is what you shift. Let's see. QN. So W is what you are shifting in if you're shifting something in. And E is whether or not it's enabled. So so if L is 1, then you load the value of R. Otherwise, if it's enabled, then what you do is you shift and you shift in the value of W. So when you look at the next page in your textbook and you see that it is instantiating these shift registers, you're using 2 shift registers to hold the numbers, and so the numbers you would load A and B, those are going to be what you map to switches. Reset is when you reset, that's when you load it. That's when you actually load that value into the register. And 1 is saying it's always going to be enabled. That's the binary number 1. 0, that one was for, oh, what you're shifting in. So we are shifting in for when we're getting our values out, when we're getting our bits out from A and B, we're going to shift in a 0 into the empty spots. And for the sum, what we're shifting in is S. That's our sum bit, so we're actually shifting in the sum. So that's where that one's coming from. And then QA is the entire number, QB is the entire number, and sum is the entire sum from what you have so far. And QA and QB, I say the entire number, it's the number that you have after you have shifted something out. So let's take a look at the things that we would need to change to turn this from a Mealy machine to a Moore machine. Right now it's a Mealy machine, and you would really need to go back and read or look at the lecture to see more about how the serial adder works. But your lab says that you need to use the states as in this state diagram on this page. So you're going to have 4 states, G0, H0, G1, and H1. And those correspond to, since it's Moore, it's what the sum is, and it's the sum of the previous 2 bits, and then what your output is going to be depends on whether or not you had a carry or not. And so if you did not have a carry, then you're in state G. And so if you look at state G, when you add together the values 0 and 1, or 1 or 0, you expect to get a sum of 1. So your next state would be 1. And so these are the values that you're inputting. And if you do not have a carry and you get the values of 0, 0, then your next state would be 0 because your sum is going to be 0. if you don't have a carry and you get 1, 1, then your next state is going to be 0, but you'll have a carry. So you'll move over to the H state, and H state has a carry. So what these states are is G, no carry, and H, you have a carry, and H0 and G0 means your sum is 0, and H1 and G1 means your sum is 1. And so those are the states that you're going to have. So how are we going to adjust our code? So this code you can pretty much leave as is, except you'll need to change your parameter where you have 3-bit numbers, so n is going to be 3. And I don't think I changed anything else on that. Now you have, when you go to your Verilog, you will have 2 modules. So you'll have your module, your shift module, and I do believe I did just copy that directly. Now, if you are like me and you actually have a PDF of the book, you want to be careful when you copy because some characters don't copy. For instance, this character, the or, does not copy, and well, I think the other characters that don't copy you don't end up using, but so if you were to just copy the PDF here, then the exclusive or does not copy. I'm not sure if the and copies or not, and the not does not copy, but those are, you're going to change those anyway, because the big thing that changes here are your states. So this only has 2 states because it's a Mealy machine. So let's see what else would have to change here to change this from a Mealy to a More. So you'll still have A, B, reset, clock, and sum. I'm going to stop here, and I am going to show you how this works. So I'm going to stop this video, and then I'm going to demo what the board is going to look like, and then we'll come back and talk about what to do. So this is just going to show you the basic idea. Yours does not have to be exactly like this. You do need to have a reset. So I have this switch. I made this switch all the way on the left, the reset. So when I press that, and then I advance the clock, and I have the clock is the bottom button here, it resets, and then I turn that back off. And then I have these 3 switches are for A. Now just to help me, I also mapped the LEDs so I could see which ones I had turned on. You don't have to do that. So for A, I'm turning on the 1st and 3rd, so that would be the number 5. That's the 1s and the 2s and the 4s, that's 4 and 1, that's 5. And then I skip a switch, and then the next 3 are for B, and I'll make that one 0, 1, 1. So I have these 2 are off and that one's on. And now when I press the button, it actually does not ordinarily show the what the sum is until it gets all the way to the end. You can if you want, but the 3 LEDs, I have the 3 LEDs at the end showing the sum. You can use whichever LEDs you want, but as I press the button, what numbers did I have here? I had 5 and 1, so I should get 6. Or did I? I had 5 and 1, so I should get 6. And I don't, and I get 4. And that's not good. One thing to be aware of is that sometimes these buttons are not debounced, and so sometimes you do get errors because it doesn't actually catch the positive edge. And so I still have the 5 and 1, and then I reset, and I went back and I did it again, and this time I got the value of 6. And so you can always try that if it's not working. It could be that you just need to try another value. Now it is going to be it is 3-bit addition. Let me reset again. And so with 3-bit addition, if you get a number bigger than 7, it's going to be modulo, it's going to roll over, so it's mod 8. And so, like, let's see what happens if I add together the number 6 and 2. So that's 8, so that should give me 0. Let me reset first, and now turn off the reset, and now advance the clock, and I get 0. So because 6 plus 2 is 8, 8 mod 8 is 0. If I did, so 6 and 2, what about 6 and 3? That'd be 9. 9 mod 8 is 1, so I should get 1. So let me reset, and then press the button. And you can see that the LEDs advance to show what the sum is, the intermediate sum. And then I just have the 7-digit display show at the end. And then just one more time, let's do 3 and 2. You can see the LEDs. Did I do 3 and 2 or 3 and 1? 3 and that is 3 and 2. It's supposed to be 5. Let me see. Reset. No, that's 3 and 1. Sorry, that is 3 and 1, which should be 4. Yeah, because this is, that's a 1. So it is supposed to be 4. Okay, so now back to the code. So let's think about the things that are going to change here. So first of all, your variables are only 3 bits, and so instead of being 7 to 0, you only need them to be 2 to 0. So you'll have that. Your sum is also only 2 to 0. And I believe I did not have output wire. I think I just had output. Let me see. Yeah, just output sum. These AL and BL, that's what I was using for the lights to show the LEDs for A and B, so you don't have to have that. Okay, and then let's look at what else we have. So we've got this variable count. The whole point of the count variable is you have to count how many times you shift the register. And so you need to have as many bits as you would need to count. So if we had 8 bits, then we would need count to be able to go up to the number 8. And if you look in this code right here, it says if reset, then count equals 8. Else if run, count equals count minus 1. And so you're counting down to make sure you get all the bits. Now this is a little sneaky here, because for a melee machine you needed to have this count equal to the number of bits. A Moore machine, if you remember, a Moore machine is going to have one more state. And so if we have 3 bits, then we need to set our count equal to 4 to start off with in order to make sure that we get all the way to the end. So that's hint number 1 of things that are going to be different. What else is going to be different? So the big thing that is going to be different is going to be obviously right here, because that's where you have your cases. Now the other thing that is going to be different is your output, because you need to output your sum to some LEDs. And so when you do your constraints, you will need to make sure that you have the clock constraints that correspond with the button. And if you remember, you can get those from the Verilog. Let's see. So if you go to the course and you go to lab assignments and you go to using Vivado to program the Basis 3 board, and you go almost all the way to the end. So it's right here. That's where you get the code for having the constraints for the clock. If you want to get the template that has all of the other constraints, I put a copy of that in the SI resources. So if you go to SI resources and go to constraints template, you can get all the constraints. So you don't want to use this clock signal, you want to use the one from the other one. And you'll want to use the switches. You'll need to use 3 switches for A, 3 switches for B, and 1 switch for the reset. And you can use whichever ones you want. So you'll have A0, A1, A2, B0, B1, B2, and you'll have reset. So you see A0, A1, A2, B0, B1, B2, and a reset. For your LEDs, you only have to have 3 LEDs, so you can pick 3 LEDs, and those are going to correspond to some 0, some 1, and some 2, and you will see those update every time you press the button. It'll update. You're also supposed to display your sum on the 7-segment display, so you'll need the 7-segment display, and you'll also need the ANs, so you'll need all of these and those. And I always call my 7-segment display variable seg, just so I don't have to rename these and AN, but you can call it whatever you want. So that's going to be similar to the lab where you did the 7-segment display. Okay, so going back now. Oh, I think I was going to show you this earlier. So you're going to have 2 modules. You'll have your module that's your serial adder that you're going to change up to have the 4 states instead of just the 2 states like in the example. But you're also going to have the module that is the shift register, and that's just going to be exactly the same as what's in the book. Do notice that the variable name, if you copy it straight from out of the book, is clock, C-L-O-C-K. So when you put in the constraints on this top constraint, make sure you put in capital C-L-O-C-K. That has to be the name of the clock. And right here, that needs to be clock as well. All right. And then, is there anything else on here besides? Okay, so before we get to the logic part here, the other thing that you'll need to add is to display the 7-segment display. And so that's going to be pretty straightforward. So you'll want to have, I put it in its own little always block. You could put it in some other always block if you wanted to. I just put always at star. That just means always do it. You don't have to have this. I just had if count equals 0. I'm just going to take that out for now so you don't have to worry about it. So you need to tell it which display, so you have to give it a value of AN, and then you're just going to have a case statement based on sum, and based on sum, whatever sum is, you're going to have seg, or whatever you call the variable, is going to be your string that corresponds to your 7-segment display. Now, I make my numbers, like A and B, I have 2:0. That means that when I you don't have to worry about those. Okay, so I have A and B as 2:0. So what that means is when I map these to switches, I'm going to map a switch to the right to be A0, and then this one is going to be A1, and then this one is going to be A2. And then what that means is these are in the place values, the binary place values. This is the 2's place, or the 4's place, the 2's place, and the 1's place. And so 1, 0, 1, for instance, would be 4 plus 1 is 5. And so when I write it as 2:0, that means that this place, that's the A2. Now notice I did seg and AN opposite, and that's just because the way I think about this is I think of this as when I'm writing out, well, I guess 0, 1, 2, 3, 4, 5, 6. When I'm writing out the string, this is just the order that I think of it in. And so if I wanted to make a 3, for instance, then I'd want to have zeros in 0, 1, 2, 3, and 6. So 0, 0, 1, 2, 3, and then 4, 5, and 6. And so that's just the order that I do it in. So I talked about the 7-segment display. So this is just a little thing to add in. Don't stress on that. That's not the most important thing, because what is important is that your sum LED lights light up. That's important. Okay, so now let's talk about the logic. I'm trying to think if there's anything else. Don't think so. Okay, so now let's talk about the logic. So we're going to have 4 states. You're supposed to use the same states as in the textbook. So G0, G1, H0, and H1. Now you can have them you can assign them however you want. This is just showing you how I did it, but you can assign them however you want. And then you're going to have in your always block, instead of just G and H, you're going to have G0, G1, H0, and H1. And now let's look at what our state diagram has. So our state diagram has you will have the output depends only on what state you're in. And so when you have your case statement, you'll have case Y, because that Y is telling you what your current state is. So case Y. And then I'm just going to show you one. You have to figure out the others on your own. So the first thing that you can do is you'll say what your output is, what S is. And so for G0, S is equal to 0. It tells us that right there. And then what is our next state going to be? Well, that depends on what our input is. Now, where is our input coming from? So our input is coming from the last bit, or the 0th bit in our values for A and B. So remember, we have A and B are these 3-bit values, and we are getting this bit, so that would be QA0 and QB0. And then what our next state is going to be depends on those. And so if you look at your state diagram, if I'm in state G0, if QA0 is 0 and QB0 is 0, then I'm going to stay in state G0. So I make a case, and my case is based on QA0 and QB0, and then I will have my 4 possibilities of those, 0, 0, 0, 1, 1, 0, and 1, 1. And then I say what my next state is going to be based on those values, and you can get those off your state diagram. And so from your state diagram, your next state, if you have 0, 0, your next state is G0, so Y is G0. If they're 1, 1, your next state is H0, and 0, 1, and 1, 0 goes to G1. So you'll do something similar for the other states. So you just will say, this is how you determine what the state is. So you'll have your outside case statement that's based on the current state. So you'll have, if your current state is G0, and then if your current state is G1, and then if your current state is H0, and your current state is H1, and then within each one of these, you'll say what your sum bit is, and you'll have a case statement to say what your next state is. Oh, one thing not to forget, because I did, and it was driving me crazy. I couldn't figure out why my 7-segment display was not lighting up. You will have to add your 7-segment display to your outputs. You don't need this AL and BL, but you will need your AN and SEG to your outputs. So you'll need to have those, and you'll need to have them listed here. But don't forget to put them in your outputs the way I did. I forgot that, and it was driving me crazy because I couldn't figure out why it was not lighting up. Okay, and those ALs and BLs, those are not necessary. It's all the same, right? Except for the AL, BL, and then you define the parameters. I believe that your shift, those are going to be defined the same way as in the code in the book. I don't think there's any change there. And you have your always block, and we talked about that. And you do have to figure out the other cases. And then you could probably put the 7-segment display in the other always block, but I did make it its own always block, and you don't need to worry about that if. Positive edge clock, I think this was exactly the same. Do be careful with the count, what that needs to be. And other than that, I think that should help you out a lot. So conceptually it's not that hard, but I did run into some problems when I was doing it with the little things that I missed, such as making sure that I had the count the right value, and that my case, that the case is based on QA0 and QB0, because when we're looking at what bits we're adding together, well, that's, I apparently already said it. It says right there, so I'd be repeating myself. Yeah, so this part in here, that's the part that's completely different, and most of the rest of it is the same. All right, well, good luck. Email me if you have questions. I'm going to be at the Eclipse all day Monday, but hopefully you'll take a look at this before then.